Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about mass number versus atomic mass. And I'd like to move into average atomic mass as well. Now, if you are still working on a mass number versus atomic number, I do have a previous video that you can take a look at that talks about mass number versus atomic number. Okay, they're a little bit different from what we're talking about today. All right, so if we're going to talk about this, let's redefine the mass number. So if you have an atom, okay, let's talk about the aluminum atom. The aluminum atom has 13 protons and 14 neutrons. So if I were to draw a little picture of that, I have 13 protons, and we like to use P positive to represent protons. I have 14 neutrons. We like to use an N0 to represent it. P for proton, N for neutron. Protons are positively charged, hence the positive, and neutrons are neutral, hence the 0. So these two together make up the nucleus of my atom. Now we know that atoms are electrically neutral. Okay, they have a total charge of 0. So if you've got 13 positives in your nucleus, that means you have to have 13 electrons zipping around on the outside of your nucleus. And we do like to use the symbol E for electrons, and we do like to use the minus because electrons are negatively charged. So you've got 13 positive protons, 13 negative electrons, and you've got 14 neutrons. If we talk about how heavy these are, protons and neutrons are roughly the same mass, and they are way heavier than the electrons. Okay, if an electron weighs like 1, a proton and neutron would weigh 1,740. Like they're almost 2,000 times as heavy. So when we talk about mass number, we are saying, what is the number? Can I count how many protons and neutrons I have? So for this one here, my mass number would be I have 13 protons plus I have 14 neutrons, which gives me a total of 27. So in this atom, I have 27 things that are considered to be heavy. 13 heavy protons and 14 heavy neutrons. Okay, so together I have 27 things that are heavy, that are massive. So your mass number is the number of protons plus neutrons. Now, this is where it gets a little confusing because I also want to talk about atomic mass. And that's the mass of an atom or the mass of one isotope. Okay, so this would be, hey, if I pulled out a scale and I put it on the scale, how much would it weigh? What would its mass be? Okay, so you have to be able to tell them apart. And it's unfortunate that their names are so close. Mass number is the number of protons and neutrons. This is always going to be a whole number. It's like asking how many boys and girls are in a class. So if you look around a classroom, you say, oh, I've got 13 boys and I got 14 girls. Atomic mass is like you put something on a scale. So if you put something on a scale, the chances that it's going to be a nice whole number, like it's going to weigh 12 grams or 13 kilograms, probably not going to happen, right? It's going to be a decimally number. So when I talk about masses, these are going to be decimal numbers. Mass numbers are whole numbers. Atomic masses tend to be decimals. Now, I do have a small issue. If I had a single atom in my hand, a single atom is so tiny that you wouldn't be able to see it. If you could somehow put that single atom on a scale, it's so tiny that you wouldn't be able to weigh it. It's too small, right? There is no scale accurate enough to be able to measure it. So what we decide to do is sort of a comparison, okay? So we have this scale here. There's no numbers on it, but it has two sides to it. If you put an object in this side, the scale will tip towards the heavy object. If you put an object on the other side, it'll tip towards the heavy object. And if you put the exact same object on both sides, then it does balance. Okay, it's one of those where you have to add objects to both sides, and if the two masses match, then your scale will balance. Now, I need to choose something to put over here. So what we do is we choose something that's near and dear to our hearts. We are organic people. The majority of the things on the planet that we consider interesting, plants, animals, birds, they're all organic. And if you look at an organic molecule, the thing that they all have in common is that they're all made out of carbon. So carbon is the basis of life on this planet. So if you read science fiction, it's the reason why they talk about carbon-based life. All of the organic molecules in your body, proteins, fats, like DNA, it all has carbon. Now, if you did watch the last video that talked about isotopes, we did say that you can have different isotopes. So carbon comes in 3 flavors. You can have 6 neutrons, which makes it carbon-12. You can have 7 neutrons, which makes it carbon-13. Or you can have 8 neutrons, which makes it carbon-14. The one that is the most stable is carbon-12. Carbon-12 has 6 protons and 6 neutrons. Right? 6 plus 6 gives me a mass number of 12, and so carbon-12 has a mass number of 12. So this one here is the most stable of all carbons. If you have it, it'll sit basically there forever. So we've decided that this is going to be our standard. We are going to put a carbon-12 atom right here on this side of the scale. Okay, that's what we're going to use to measure against. And then on the other side of the scale, we're going to put things that we want to know the mass of. We want to weigh. So if you have 2 different atoms and they balance out perfectly, then the mass of this atom would be exactly the same as the mass of a carbon-12. Okay, they would be the same. If you had to put in, say, 2, you had to put in 2 atoms because they are really tiny in order to match it up with the carbon-12, then you would say that this is half as heavy as a carbon-12. Okay, everything is going to be measured based on how heavy a carbon-12 is. Now, that is a little bit cumbersome, right? For me to say, oh, it's twice as heavy as a carbon-12, or it's 3 times as heavy as a carbon-12, or it's half as heavy as a carbon-12, right? That just, it's cumbersome to say it. So what we've decided is that we're going to assign this a weight. We are going to say that if you had a scale and you could actually measure a carbon-12, we're going to say it weighs exactly 12. Now, we just made that up. We decided if you got a carbon-12 and you put it on a scale and you measured how much its mass was, we decided to call that a 12. Now, it's not 12 grams because it's too tiny. It's not 12 kilograms because it's too tiny. So we decided that, hey, if we can assign a number, we can also make up our own units. So we call this 12 atomic mass units. Or for short, 12 AMU, atomic mass units. So we've decided that if you have a carbon-12, it weighs exactly 12 atomic mass units. Which means that if you weigh half as much, you only weigh 6 atomic mass units. If you were to weigh twice as much, you'd weigh 24 atomic mass units. Okay, everything is going to be measured based on carbon-12, and we've decided this is how much it weighs. And we literally just decided that. We were like, hey, let's make it weigh 12. Okay, so if we take a couple of examples, it turns out if you put carbon-12 versus magnesium-24, okay, the number of protons and neutrons in this magnesium would be 24. Turns out that you would need 2 carbon-12s to balance 1 magnesium. Okay, if you had 2 carbon-12s and 1 magnesium-24, they would balance out perfectly. Well, 1 carbon-12 weighs 12 atomic mass units. The other one also weighs 12 atomic mass units. So together they would weigh 24 atomic mass units. So if you look at your magnesium-24, if this side weighs 12 atomic mass units and they're totally balanced, then the magnesium-24 would also weigh 24 atomic mass units. Okay, let's talk about helium versus carbon. If you had a carbon-12 on this side of your scale, in order to balance it, you would need to have 3 helium-4s, right? It's got to be 3 of those. So if this side weighs 12 atomic mass units, that 12 atomic mass units has got to be divided into 3 pieces, right? 12 divided by 3 is 4. So this would be 4 atomic mass units. This would be 4 atomic mass units. And this would be 4 atomic mass units. So in the world of elements, when we talk about how much one weighs, when we talk about the mass of an atom, it's all based on a carbon-12 being 12 atomic mass units, and then everything else is weighed based on it. Now, this shouldn't surprise you a whole lot, because basically what we're saying, if we come back, carbon-12 has 6 protons and 6 neutrons. If we say that it weighs 12, basically we're saying a proton weighs 1 and a neutron weighs 1. Okay? So if you've got magnesium-24, you've got 24 protons and neutrons. If each one weighs 1, then the total should be 24. Right? If you're talking helium-4, helium-4 has a mass number of 4. That's the number of protons plus neutrons. If a proton weighs 1 and a neutron weighs 1, and you got 4 total, then they should weigh totally 4. Now, you're going to find that there is some decimal issues here. Because what have we neglected? We've neglected that there are electrons kind of flowing around the outside. They don't weigh a lot, but they do make a contribution. Okay, so when we talk about the mass of an isotope or the mass of an atom, it will be pretty close to the mass number, but it may not be exactly the same, right? So if you had a magnesium-25, it might not weigh exactly 25 atomic mass units. It might be like 24.98 or 25.02. It'll be close, but it probably won't be exactly the same. Okay? And that's part of the reason why these are a little confusing, because your mass number and atomic number tend to be pretty close together, right? If your mass number is, say, 21, then your atomic mass is going to be pretty close to 21, right? It could be like 20.996. It could be 21.003, right? But it'll be close. The biggest thing here is to keep the two of them separate in your mind. Mass number is counting. Atomic mass is weighing. Okay. So let's talk about how you get the numbers on the periodic table. Because if you go and look up magnesium, let me pull out my periodic table. Right, if I pull out my periodic table, it tells me that magnesium, okay, the number here in the top corner says magnesium is 24.31 atomic mass units. I just told you that a magnesium-24 weighs 24 atomic mass units. So where did this weird number come from? And the place that it comes from is a weighted average. Okay? Think of the last course you did. Okay? You're in the course and you're going to be writing like tests and you're going to be writing exams and things. Okay? Let me steal just a bit of this. Okay, so let's say you're in the course. You wrote your first quiz and you got 100%. You were feeling very, very happy with yourself. You write the second quiz and you got another 100%. You're like, both of these are going on my refrigerator because I am so proud of them. You write another quiz and you get another 100%. You're like, I'm on fire. I am just acing this course. This course is the best. Then you write your test and you get like 25%. It was a terrible, terrible day. you didn't get any sleep. On the way to school, you like fell down and hurt your leg. It wasn't your best day. So now if I wanted to do an average of this, right, I wouldn't just do a straight average and say, oh, it's 100 plus 100 plus 100 plus 25 divided by 4. Right? I wouldn't say my average is 81% because I know that tests are worth more. Right? Because the tests are worth more, this mark is going to be way lower than the average. It's going to be a weighted average because quizzes are weighted pretty lightly, right? They don't have as big an impact, but your test is weighted heavily. It's worth a much higher percentage. Okay, so your average probably won't be 81%, right? Your average will probably be closer to 60%, right? Because your test is worth so much. We're going to have the same thing when we try and find the average weight or mass of a isotope or an atom. Okay, so if we're going to do average atomic mass, it is a weighted average of the masses of the isotopes. And for example, let's talk boron. If you have a boron 10 means you got 10 protons and neutrons. A boron 10 weighs about 10 atomic mass units, right? Because a proton weighs about 1, a neutron weighs about 1, throw in a couple of electrons, and so a boron 10 weighs about 10 atomic mass units. But you can also have boron 11s, right? A boron 11 has 11 protons and neutrons. It has 1 extra neutron. So if I were to weigh this, because you have 11 protons and neutrons, it's going to weigh roughly 11 atomic mass units. Percent abundance. 19.9% of all borons that you see are boron 10. 80.1% of all borons that you see are boron 11. Okay, so think of it like you go into the store and you like scoop out candy out of a bin. And let's say in that container there's like more than one type of candy. So you've got maybe raisins and you've got some sort of nut. So when you scoop it up, you're going to have a mixture of both. If this was my mixture, I'd have basically 20% raisins and 80% nuts, right? That's going to be my mixture. But when you buy it, you don't weigh them separately. You don't say, oh, 20% of them weigh 10, 80% of them weigh 11. When you take it up to the cash to get it checked out, they're going to weigh the entire thing and basically give you kind of an average, right? That's what we want to do here. I would like to have a mass for an average boron. So when I take my scoop of borons, I've got a mixture of both. I got some boron 10s, I got some boron 11s, and what I'd like to know is, in my scoop of borons, what would be the average mass of them? And a little formula we have for that says take the percent abundance and multiply it by the mass. So we're going to take percent abundance and multiply it by its atomic mass. This little sign out in the front is a sigma. It means add them all up. So you'll do the multiplication for the first isotope, then you'll do the multiplication for the second isotope, and then you'll just add them up. And that'll give you a weighted average. So you know the average between 10 and 11 is going to be somewhere between 10 and 11. But because most of them weigh 11 and very few of them weigh 10, you know that it's not going to be exactly in between, right? The average between 10 and 11 is not going to be 10.5. Because the majority of them are heavy, the average is going to be closer to 11. So if I had to make a guess, I would say the average here might be like 10.8. Okay? Not in the middle, more towards the heavier one because there's more heavy ones. If I had like a third isotope and a fourth one, I would do the multiplications and then I'd add them all together. Okay, so let's do that. If I want to calculate the average atomic mass, my formula says take the abundance and multiply it by the mass of each isotope. So abundance, 19.9% times the atomic mass, 10.013 AMU, plus, do it for the second isotope, 80.1% times the mass of the second isotope, 11.009 AMU. Now, if you've done math, you know that you're not allowed to multiply a percent by a number. You have to turn the percent into a decimal. In order to turn percents into decimals, you have to divide it by 100. And divide it by 100. Now, for these two here, your chances of making a mistake are pretty low, because most people can turn 19.9 into 0.199 as a decimal, right? Divide by 100. The ones that are going to cause you trouble are when you have a percentage that's less than 10, right? If I had 2%, 2% becomes 0.02, right? And that's where people run into trouble. So if you're worried that you're going to make a mistake, use your calculator, right? 19.9 divided by your 100 gives it to me as a decimal. And then you don't have to worry about making mistakes. All right, so that's times my 10.013 atomic mass units plus 80.1 divided by 100 is 0.801 times 11.009 AMU. So if we do the calculation on our calculator, so I got my 0.199 already in, times 10.013 plus 0.801 times 11.009. My calculator tells me the average is 10.811. Now, if all of the masses were originally in AMUs, this would be in AMU. So when you take a scoop of boron, there's not a single boron atom that's going to weigh 10.8, like none of them. Because borons will either weigh 10 or they'll weigh 11, right? That's the two different flavors. Boron 10 weighs about 10. Boron 11 weighs about 11, right? So if you actually had a scoop of boron, some of them weigh 10, some of them weigh 11. But if you talk about the average of them, the average is 10.8. It's kind of like when we talked about your quizzes, right? If you talk about quizzes and tests, you got a bunch of quizzes in your hand, all worth 100. You got a test in there too, and it only got a 25%. So if you wanted to get an average mark, the average mark, say, was 60. The 60 is not the mark on your test. It's not the mark on your quizzes, but it is representative of the entire body of work, right? You did quizzes, you did tests. Overall, how did you do? You got about a 60. Same thing here, right? Nothing in here weighs 10.8, but on average, an average here would be 10.8. And if you look at your periodic table has that number. Now, depending on what your periodic table looks like, okay, some periodic tables have a lot of information. This one here has a lot of information. Names and symbols and a bunch of numbers. Some periodic tables have very little. Okay? At the very least, your periodic table will have these three things. It'll have the symbol for the element, right? The symbol for boron is B. If your periodic table is really empty, lots of times it won't even tell you the name, right? So it'll tell you the symbol is B, but they won't tell you that it's boron. They will tell you the atomic number, the number of protons. And they do like to give you the average atomic mass. Okay, average atomic mass. The average atomic mass is the decimal number. Okay, it'll always be a decimal number. And this is the mass of an average boron. There you go. All right, let's say we try a second problem. Let's say we talk about magnesium. Magnesium comes in three different flavors. There's magnesium 24, magnesium 25, and magnesium 28. Whoops, I believe that's a typo. That should be magnesium 26. Now, if you were to take each one of these and you could put it on like a little tiny balance and weigh it, magnesium 24 weighs about 24, a little less actually. Magnesium 25 weighs 25, again, a little less. And a magnesium 26 weighs 26, or a little bit less, right? These numbers have to be given to you. There's no way that you can guess them with that amount of decimal places. Like I could guess that a magnesium 24, if I put it on a scale, would have a mass of 24. but there's no way that I could guess that it would be 23.985. Okay? So if I want to calculate the average atomic mass. Now, I already looked it up on my periodic table. I already know what the answer is going to be. The answer is going to be 21.31. So when we do this calculation, I should be able to check my answer at the end. Now, I can kind of make a prediction here. You'll notice that the majority of the magnesium weighs about 24. 10% weighs 25, and about 11% weighs 25. Think of it like your tests versus your quizzes, right? You did some quizzes worth like 11%. You did some assignments worth 10%, and you did your tests, and your tests are worth 80% of your mark. Well, what's going to dominate your mark? Your tests, because they're worth so much. So out of these three numbers, the one that's pretty close to 24, that's the one that's going to dominate. So when I take an average of 24, 25, and 26, my average is going to be very close to the 24 because most of it has a mass of 24. Like 80% of it has a mass of 24. Okay, so let's do the actual calculation. The formula said, take the abundance and multiply it by the mass. So abundance times mass, abundance times mass, abundance times mass, and then add them all up. So this would be 78.99% times 23.985 AMU plus 10.00% times 24.986 AMU plus 11.01% times 25.983 AMU. Now, just like the last time, you can't multiply if you got a percentage. So this got to turn into a decimal, this got to turn into a decimal, and this has got to turn into a decimal. So that would become 0.7899 times 23.985 atomic mass units plus 0.1000 times 24.986 atomic mass units. Now, see how this 10 had 3 zeros at the end? I decided to keep 3 zeros at the end because somebody went to a lot of work to measure this to 2 decimal places, right? To figure out that 10% of all magnesiums are this one, to get that number to 2 decimal places, that's pretty impressive. So I'm going to honor that by keeping all the zeros. Now, your calculator will just throw them away, but in the world of science, if you got a bunch of zeros at the end, we do like to keep them. And if I divide this one by 100, that gives me 0.1101 times 25.983 atomic mass units. The other thing is consistency, right? 4 decimals, 4 decimals, 4 decimals. 3 decimals, 3 decimals, 3 decimals. Like when we do these, I do like to have each piece of it kind of matching up with the rest, right? If I'd gotten rid of these 3 zeros, that one really would not have matched the rest. All right, let's put it in our calculator. 0.7899 times 23.985 plus 0.1000 times 24.986 plus 0.1101 times 25.983 gives me an average of 24.305 atomic mass units, right? If they all started as atomic mass units, they end up as an atomic mass unit. And you can see my periodic table just rounded it off to 2 decimal places, right? If you round it off, the 5 makes it round up. That's why my periodic table had 24.31 atomic mass units. Again, there's not a single magnesium atom that weighs 24.31, right? A bunch of them weigh roughly 24, a bunch of them weigh 25, and a bunch of them weigh 26. But if you throw them all in and give me an average, what does an average atom weigh? This is the average. So that's my average atomic mass. All right, let's try one more. For this one here, I decided to leave something out, right? I tell you the isotope, I tell you the abundance, because again, you can't guess that, but I did leave out the atomic mass. The atomic mass of the isotope. I left that out. And the reason why I left that out is because sometimes these problems will do it on purpose. And what they want you to remember is, hey, if I got a copper 63, the 63 means I have 63 protons and neutrons. And if I have 63 protons plus neutrons, that means it's going to weigh roughly 63 AMUs. Probably not exact, right? If you actually went on the internet and you looked it up, a copper 63 will weigh close to 63, but probably not exactly that. But if you got nothing else, it's a good estimate. Now, if you got a copper 65 is going to weigh about 65. Now, let's take a prediction of the answer. If this was a nice 50-50 mix, if you had half and half, then the average should be a real average, right? 63 plus 65 divided by 2, the average would be about 64. But because you have more of the light one, right? The one that weighs 63, you have more of it, and the one at 65, you have less of it. So my average is going to be closer to the low side. So maybe it'll be like 63.8. Okay, it's not going to be exactly in the middle of the two because you have more of the light one, so it's going to be more towards the light one. Okay, that's just a bit of a prediction. You don't need to do the prediction, but it does help me feel better about my answer. Like if I get an answer that's 63.8 or 63.7, I will feel more confident in it. Okay, so if we do our calculation, average atomic mass. It's the percent times the mass, times the mass, and then add them up. So this is 69.17% times 63 atomic mass units. Not as many decimal places as I like, but when you're stuck, you go with what you have. This is 30.83%. And the mass that goes with that isotope is 65 AMU. Again, I'd like more decimal places, but that's the best I have. So for a third time, let's turn those decimals into, those percents into decimals by dividing by 100. So that would give me 0.6917 times 63 atomic mass units, 0.3083 times 65 atomic mass units. And if we pull out our calculator, 0.6917 times 63 plus 0.3083 times 65 gives me an answer of 63.6166 atomic mass units. Now, let's round it off, because that seems like an excessive amount. So if I rounded it off there, let's say I wanted to just keep 2 decimal places. The thing that I've gotten rid of is bigger than 5, so I should round up. So that would give me 63.62 atomic mass units. Now let's talk about my prediction. I predicted that the average was going to be towards the small side. It was going to be 63 point something. I got 63.6 and I had predicted 63.8. That's pretty close. It's on the lower side, so I'm good with that. Now, if we compare it to the number that comes straight off the periodic table, the periodic table, when it did the calculation, said that the average atomic mass was 63.55. And when they did this, they used the perfect values of atomic mass, not just the approximations. But even going with the approximation, we're still pretty close, right? This is 63.55, this is 63.62. If you think of it as prices, right? If you bought something for $63.62 versus $63.55, that's not really a big difference. Okay, so the approximation will get you close to the right answer. If you want to get the absolute right answer, then the problem will have to give you the masses of the isotopes. So once again, thank you for joining me here at Chemistry with Dr. Clark. And if you want to go back and review mass number versus atomic number, that would be the previous video in the series.